Ladies and gentlemen, can Whitsitt be honest? He has this little verbal tick during debates where he'll say something like, "Bro, quick honesty test. If my Navy pilot buddy saw K2 from 300 miles away in Afghanistan and it was at eye level, would it debunk the globe, bro?" And my answer is always, sure, bro. You know, pilot's at 28,000 feet, K2 is 28,000 feet, and it's 300 miles away. That would be a globe killer if you actually had any concrete evidence. The hilariously chicken shit thing, though, is that Whitsitt won't commit to the antithesis of that. So he won't commit to saying flat Earth is dead if we do measure 8 inches per mile squared of drop. And the title of this video is a bit of a nod to Betteridge's law of headlines, which states that any headline that ends in a question mark can be answered by the word no. But let's give Austin the benefit of the doubt for now and see how it pans out. So no doubt everyone watched the debate he had with Professor Dave the other day, and he gish-galloped his way through his presentation as usual, which gives credence to another law of the internet called Brandolini's law. That states the amount of energy needed to refute bullshit is an order of magnitude bigger than that needed to produce it. Anyway, here was the first C2 far observation that he had on screen, so let's hear it.
Here we have a distant mountains observed from 167 miles away at less than 1,000 feet. So the target hidden height should be almost or over 11,000 feet, but the mountain's only 12,000 feet. We should only be seeing roughly 1,000 feet of the mountain. Clearly, that's not the case.
Right, so there's the claim. 167 miles away, observer height 906 feet, hidden height 11,300 feet, and elevation of the mountain 12,600 feet. And we should only be seeing 1,000 feet. And according to Whitsitt, clearly that's not the case. So let's do the analysis that Whitsitt should have done before putting this into his presentations. Okay, so I found the original photograph on the interwebs, and it was taken by an Italian dude by the name of Fabio Longaron. And on the website it says that he was in the vicinity of a little village called Pedona, but we can be a lot more accurate than just the village, so let's narrow it down. So from Pedona, this little island is in the line of sight, and it's called Isola del Tino. And what I noticed about the photo is that if you draw a line of sight from the peak of Monteviso, you'll see that it's pretty much smack bang right in the middle of that island. So we can mirror that on Google Earth by drawing 2 lines either side of the island and then another line right through the middle and extending those 3 lines for about 167 miles. And when we extend those lines back, we get to a little area south of Pedona. Those 2 white lines are actually big circles I've drawn in Google Earth. So anything in between those 2 lines will be rounded up to 167 miles. Which is the distance that Whitsitt gave. So score 1 for Austin. Well done, champ. 167 miles confirmed. But here's our first problem. That green blob right in the middle is a Google Earth polygon, and I've set the altitude of that polygon to be 905 feet. So that wiggly orange line is where Whitsitt is claiming the photographer was. Now this is an overhead view, so it's not going to make a whole lot of sense right now, but there are 2 roads in the area. There's Via per Pedona, which is at 1,115 feet, and Via Colli, which is 1,168 feet. And that's where I think the photographer was. So now from this angle, hopefully what I just said on the previous slide makes a lot more sense. There's absolutely 0 chance that the photographer has scrambled downhill amongst the forest to take a photo when he could just as easily take it from the higher road. Now, there's a very small chance that he took it at the 1115 feet elevation, but on the Google Street View, the view seems almost completely obstructed by trees. And if you're going to take a photo of a distant mountain on a globe, then it pays to be as high as possible. So I'm pretty much certain that the photo was taken from the higher elevation of 1,168 feet. So that's the first honesty test for Whitsitt. Can he admit that the observer height is too low by at the very least 210 feet, but most likely by 263 feet. Right, so let's check Whitsett's second claim that the target hidden height is 11,291 feet. Did he take into account refraction? Now, before I remove these bars and show you the answer, let's have a word from our sponsor.
I'm claiming that you haven't even actually accounted for all the variables, and you're touting your trigonometry that literally hand waves dismiss one of the most important variables when it comes to perception, which is refraction. Refraction always happens. That's why it's important. Refraction, which we immediately and adamantly claim is always present, because there's temperature fluctuation and atmospheric conditions that are consistently affecting what you perceive. Well, if you can't adequately account for refraction, you can't make a claim about the apparent location, now can you, Randy? Refraction increases proportionate to the distance, and never in your dissecting of the observations do you even account for refraction that we know for a fact to be present. And refraction, because you're increasing refractive effect proportionate to distance. So the more atmosphere you have in between you, the more refraction you have, because the more atmosphere that's there. When you just throw refraction out entirely, invoking the furthest point away in the image and saying that you don't have to account for refraction and making the baseless assertion it doesn't move it, because you showed us some really not very great images where they look to be generally the same, is laughable, bro.
It's laughable, bro. All right, we're back, and I'd just like to thank our sponsor, MC Toon. So are we ready for the big reveal? Oh no, Whitsett, what happened, bro? All right, so there's honesty test number 2 for you, bro. Will you admit that you selectively apply refraction to try and debunk globe proof, but then ignore refraction when you think it debunks the globe? That's super gamma, bro. So here's the result when you apply standard refraction and use a more realistic viewer height. You get a hidden of 8,500 feet, which brings us to Whitsett's last claim, that we should be seeing only 1,000 feet, and quote unquote, clearly that's not the case. And I agree that's not 1,000 feet, because a prediction of 1,000 feet would be strawmanning the globe now, wouldn't it, bro? So let's do the analysis that Whitsett clearly did not do and see how much we are actually seeing. And the way we do that is, first of all, find the horizontal field of view for the photo. And the best way to do that is to line it up to a U-Deutschler render, because it has the azimuths at the top. So you can see it's almost 2 degrees wide. And if you do the pixel counting, you get 1.874 degrees. And once you've got the horizontal field of view in degrees, it's a pretty simple exercise to scale it against the angular height of the part of the mountain that's above the horizon. And we get 0.304 degrees. And then we just go and plug that into an angular size calculator, and we get a total visible height of the mountain of 4,685 feet. So, just to recap, we've got our observer location, elevation, target height, the predicted hidden, assuming 7/6R standard refraction, the actual visible portion of the mountain, and then the actual hidden part of the mountain as measured on the photograph. And I'm sure the flurfs are all laughing about how the globe prediction is off by 600 feet, but still ignoring the fact that there is 8,000 feet of a mountain hidden below the horizon. And Whitsett will probably still somehow claim that this debunks the globe, which is such a gamma move, bro. So just to satisfy Jaren, who I'm sure will just say that we can move the refraction slider to wherever we like to make it fit on the globe, I'm just going to show you where we would have to move it to make it a perfect fit for the globe. And this blue line represents that slider. So on the left, we've got 0 refraction, so no density gradient. And that's silly because there is a demonstrable, measurable density gradient in our atmosphere. And what kind of gamma male would assume no refraction, bro? All right, on the right-hand side, we've got black swan conditions, and that represents light bending at the same rate as the curvature of the Earth, and that would have the effect of making everything look flat. So that's our slider. Now, where does the infamous 7/6R fit on that spectrum? That would be right here. Now, this yellow arrow is standard refraction according to Walter Bisland's Advanced Earth Curve Calculator. Now, Walter calculates this based on what's called the International Standard Atmosphere, and it turns out to be slightly stronger than Mick West's approximation. Where the real average is, who knows? Probably somewhere in the middle. Now, the big question is, where do we have to move the slider to make this observation fit the globe perfectly? Well, here's the big reveal. Dun, dun, dun! It's here, a tiny bit stronger than standard. So as I've been saying for probably 6 years now, if you're well above the surface, then us globers are going to have to stick to something pretty close to standard refraction. Anyway, refraction lecture over. Back to Whitsitt and the third and final honesty test. Can you be honest, bro? If you put in the right observer height and apply standard refraction, which model makes the more accurate prediction? Or my prediction is that you're going to be a gamma male and say that flat Earth doesn't make any predictions. You're as scared as Oakley, and that is hilarious, bro.